G'day, my name's Dave Garrett and I'm here to talk about the potential for using CT localizer radiographs for protective lead gown quality assurance. For this presentation, I don't have any conflicts of interest or disclosures to make. In many hospital imaging departments, annual lead gown quality control is performed using fluoroscopic imaging. And it's often performed by a radiographer who makes judgments on the condition of the gown while screening it. CT localizers can provide the same damage detection outcome with a number of additional benefits. In this talk, I'm going to review some of the advantages and disadvantages of using CT localizers for lead gown QC and show you a tool I made to assess the ability of a CT localizer to display damage in lead gowns. The images of this lead gown damage phantom were also a useful means of comparing damage detectability between fluoro and CT images. One of the biggest advantages of using a CT localizer is the extended field of view that you can capture. Here, you can see a full-length gown in one image. I've laid the gown out on a pat slide so I could get it as flat as possible to minimize folds or creases appearing in the image. You can capture the entire area of a pat slide, which means you can even image a complete set of gowns all at once. I was surprised that you can even see damage through multiple layers. So you can lay out your gowns as they would normally be worn, which can be helpful if you wanted to consider what organs are being exposed by damage. As you can see in this image, significant damage is quite obvious. This particular gown is like nothing I'd ever seen before, and is ultimately what I have to thank for the inspiration for this talk. Another advantage of the CT localizer is that if the table height is set so that the gown is at isocenter, the size of any damage can be measured accurately and annotations can be stored on exported images. Probably the biggest limitation of the Siemens brand scanner used here was the resolution on larger scan lengths. There's still enough detail to see significant damage, but you might want to see more detail once you find it. Here's an example of some minor damage that you can see on the same large scan length image. Again, you can see it, but not in much detail. Fear not, there is a way around it. It seems as though there's some sort of pixel binning going on in longer scans. So all you have to do to see damage in better detail is drop the length of the scan down below the threshold where the pixel binning begins and rescan the damaged region. For Siemens scanners like the one used here, the threshold seems to be at 512 millimeters. I'm not sure if the same limitation applies to other brands of scanners, so it's worth keeping it in mind. Alright, so I mentioned earlier that this heavily damaged gown served as the motivation for this talk, and that's because I dissected it to see what was going on. I was surprised to find that there was not one but two layers in the front, and it was only the interior layer that had fallen down. The outer layer was still completely intact. I also noticed that there's some sort of plastic deformation going on, like stretch marks or something, and I suspect these marks eventually fatigued into the cracks and tears that caused it to fall down. So I cut out a piece that had both cracks and deformation marks and glued it to an undamaged piece. Here you can see a photocopy scan and a CT localizer scan. Both have been windowed and leveled to show as much detail as possible, another advantage of using CT localizers. I wasn't convinced that I could see the plastic deformation on the CT image, so I decided to make another phantom. This time I took samples from parts of the gown that showed different levels of damage. I got a sample that was undamaged, one that was lightly fatigued, a heavily fatigued bit, and a piece that was cracked. I also cut a couple of lengths of the undamaged lead to provide the same attenuation in the image that you would get if you had the gown laid out as we saw it on the pat slide. I even went one step further and included lengths of the outer lining and the inner lining in case they contributed to degradation in the image at all. I found the optimal technique factors to be 80 kV and upping the tube current as much as you can without pushing the tube too hard. Here, I've made some standard deviation measurements of the pixels in each sample for a range of tube current settings, including the max setting, 345 mA. As you might expect, there is a trend of increasing standard deviation with damage, but there isn't much benefit in cranking the tube to max MA. So, could a standard deviation measurement be used to infer the presence of plastic deformation? I think it could, but it doesn't really affect the protection provided. The only benefit in my mind would be to see if this deformation exists in an already cracked or torn gown. I'd argue that it could add to the decision to remove a damaged gown from service that otherwise does not meet the criteria for retirement. So what about fluoro? I figured I might as well see what kind of images I could get using the methodology that is typically used during fluoroscopy. I had the lead on the bed so that the bed could be moved around to image different regions. I had the lead as close as possible to the detector with the grid removed and used a medium dose screening protocol. I also only used one layer of the undamaged lead strips to simulate just a single panel of the front of the gown. I was surprised I couldn't see the plastic deformation, but then I realized it could be because I couldn't window and level on the fluoro interface like I could on the CT. So I exported the images onto ImageJ and used the window and level functions to make the images that you see here. I still don't think you can see the deformation marks, but I couldn't do the same standard deviation measurements on the exported fluoro images that I did on the CT images because the field of view was so small that I had to image each sample individually, which meant each sample had different technique factors due to the automatic brightness control, and the standard deviation values wouldn't be as comparable. So to wrap things up, we saw that CT localizers can be a viable alternative to using fluoroscopy with numerous advantages like being faster and providing window and level function to increase visibility of damage. It can also be performed by anyone with a use license who doesn't need to make financial judgments about the retirement of the garment in the moment of scanning. There's minimal occupational exposure as you're not in the room. The larger field of view allows entire gowns to be captured in a single image and assessed remotely, and you can potentially predict failure in a gown that appears to have only minor cracking. Special thanks to Deb Carrick, who gave me the opportunity to go this far down the rabbit hole. And I'd like to invite not only questions in question time, but also any suggestions for further analysis methods that could enhance the detection of plastic deformation using on-screen tools like the standard deviation approach discussed here. Thanks very much for listening.